Let's continue. I have 1, 2, 3 to 4 page. But it is repetition of what we did. It's not too much. Yes, it's about uncertainty. And then after that, we are going to adjust a little bit from this chapter, but hopefully we'll finish it after exam. So let's talk about energy, time, uncertainty. So if you remember from like your modern physics class, when we introduce uncertainty, we actually don't have much arguments. We say, we observe that typically delta x, delta p is bigger than or equal to h bar over 2, right? And this comes from the observation that in quantum mechanics we have wave and particle nature mixed together, right? And if I have like a perfect wave, the wavelength is perfectly defined, lambda is perfectly defined, and from de Broglie we know p, which is h over lambda, is perfectly defined. But this wave is completely delocalized, right? I cannot go and put a position for this wave. So delta x is large, then p is determined. If delta p is small, delta x is large, and on the other limit, if I have like a perfectly localized wave, something like that, and I have like now a good, well-defined position, let's call it x naught, but now I lose the sense of momentum because I lose the sense of wavelength. So lambda is undetermined, therefore p is undetermined. Right? That's how we intuitively understand uncertainty in the elementary approach. And then we know x and p are Fourier transforms of each other, right? If you are in the position basis, x is a good number. You can Fourier transform, and there's like a p basis, and we also like connect it to like uncertainty principle. And similarly, t and omega are Fourier transforms of each other, and omega is connected to energy. Without almost giving any argument, we also say delta E, delta T is also bigger than or h bar over 2. Right? Now I want to make it these arguments just a little bit, okay. This one we already made it quite formal and we know where it comes from. I want to also do the same thing for this kind of uncertainty. So let's, for any operator Q, let's calculate d dt, expectation value of Q. If you remember, like this is quite easy, right? We did this for x in the beginning of semester, and it gave us something very useful. We noticed that p is actually an operator which is derivative. So now I want to calculate this thing, and what is this thing? I want to calculate d dt on a state psi, this q operator, but I'm not going to write it, psi. Now I can hit with derivative on this psi, I can hit on q, or I can hit on other psi. There will be three terms, and let's do that. So this is equal to, let me write it like this, d psi dt, this is q psi, plus psi dq dt, psi, plus psi q d psi dt. Good. Now I want to use Schrödinger equation, I h bar d psi dt is equal to h operator psi. I think now I understand your question. You are going to see in a little bit. Yes, what I mean. And from here I can see this one. So this is going to be then okay, d psi dt is minus I over h bar h psi, and this minus I, because it's in the bra part, will come out with I h bar, right? Anything here comes out with the complex conjugate because it's inside the bra operator. So this is going to be h psi q psi plus, there is nothing to do about this. Let me write it like this, dq dt. Actually, inside q, if there is some time dependence, formally we need to make it partial derivative, but you know, I'm like careless for these things, sorry about that. And lastly, I have the same thing here. This is going to be, so this is minus I over h bar, but since it is in the ket piece, it's going to come out like minus I over h bar psi q h psi. Good. Now let me combine first and the last term. So this is I over h bar, and you can see I can just commute it here because h is Hermitian. I can write it in the bra or I can write it in the ket, but I need to obey, right, the sequence of operators. Then this is going to be psi hq, this one, and I have minus qh psi, and this term is like it is. So this is expectation value del q del t, and this is the commutation of h and q. Then what we have is d dt expectation value of q is equal to I over h bar expectation value of h with q plus this explicit time dependence. Q HQ, right? This is correct. This one. So I just wrote this one is like HQ. Okay, good. Now, first, generally, we don't have time-dependent operators, right? There are like some specific problems that may have explicitly time-dependent operators, but 99% of the time, you never have to worry about those. So I'll just assume so del Q del T is 0. There is no explicit time dependence in Q. Then what we see is, this is the equation. And now, answer to your question, d dt, expectation value of an operator, is yes. The answer we found in the beginning of the semester was, this was 0. But in the most general case, this is 0 only if H commutes with Q. Now we see another important result expressed in terms of commutation, right? Previously we said if A and B commute, they are compatible observables. They can be measured simultaneously. If not, there is an uncertainty between A and B. And now, if H and Q are these operators A and B, we see Q is going to be expectation value of Q is going to be changing with time if it doesn't commute with Hamiltonian. If it commutes with Hamiltonian, its expectation value will be constant, right? The derivative is 0, that means it's going to be constant. That means it's going to be conserved. If this is 0, Q is conserved. Okay? Or sometimes people call it, if this is the case, if H and Q commute, we say Q is constant of motion. Good? So now your question makes sense, right? Okay, good. Thank you. I appreciate. Now let's come back to the uncertainty relation. What did we find in the first hour? It was like for any operator A, sigma A squared, sigma B squared was bigger than or equal to 1 over 2 I A commutation with B expectation value squared. Now what I want to do is I want to take A to be H and B to be Q. And from here we found what this expectation value is, right? Expectation value of, let me write this here one more time. So from here the expectation value is minus I H bar, and this is gone. Then what I have is sigma H squared, sigma Q squared is bigger than or equal to 1 over 2I minus I H bar d Q dt, and this entire thing squared. So i's nicely cancel. And at the end, now I need to define an uncertainty, right? Let me do it in two steps. First, take the square of both sides, sigma h, sigma q should be bigger than or equal to h bar over 2 d expectation value dt. And now for this one, okay, I will call it now standard deviation of Hamiltonian is going to be delta E, but for delta Q I'm going to define sigma of Q, this is for delta T I'm going, so I need to choose an observable. For delta T I'm going to choose sigma of Q divided by d expectation value of Q dt. Okay. So what is the meaning of this? So this is one standard deviation, and this is time development or change in time. And delta t is, I define delta t as the required time for expectation value of Q to change one standard deviation, right? That's not like some variance, something else. I have to define it this way. If I do this, then I have delta E, delta T bigger than or equal to h bar over 2, which is energy time uncertainty. Okay. So you can, there are some applications in the book. If you are interested how to choose this delta t in a given problem, you can look at that. But I want to do another thing here, and then I'll finish it afterwards. Let's consider Q to be x, and H, let's keep it general, like some p squared over 2m plus v of x. Now I need to calculate commutation of h and x, because that's how I have uncertainty defined here, right? I need to calculate the commutation. And this is going to be equal to p squared over 2m plus v of x comma x. So what is the commutation of v of x with x? Right? 0, right? X and x commutes. X and any function of x also commutes. So this is automatically 0. Nobody has to do anything about that. And the second one is 1 over 2m p squared and x. I think different people do this calculation differently. Let me do it. P squared x minus x p squared. And here I have p x. And I want to use xp minus px is equal to IH bar. So this is usual position momentum uncertainty. Then what I can do is like I can write this as x p, and there's one more p here, p plus IH bar px, right? So let me write it one more time. So this is px. So this is and from here I know px is equal to xp minus IH bar. So this is xp minus IH bar. Did I get that right? xp minus IH bar, that's correct. And I multiply with p and p. Now you can see I have one more px here. So this is going to be xp minus IH bar p. So this entire thing is going to be equal to xp squared minus I have IH bar p, IH bar p, IH bar p, and lastly minus IH bar p. And this plus xp is going to cancel this one. At the end, commutation of p squared with x is going to be minus 2i h bar over 2m times p. Therefore, so d dt x is equal to I over h bar. So this thing, where did I have it? So this I over h bar and the commutation's expectation value. So this is minus 2i h bar over 2m commutation expectation values, expectation value of p. So h bars cancel, 2's cancel, I times minus I is 1. Then I find d dt expectation value of x is equal to expectation value of p divided by m. What's that?
Ehrenfest rule.
Yes, this is sometimes called Ehrenfest theorem. Similarly, okay, here maybe I can give this as an exercise for you. This is exercise. Choose q is, for this result we choose q is equal to x. We can choose q is equal to p, and then we are going to find d dt expectation value of p is going to be, so this is a little bit trickier but hopefully not awful. Let me write it, and then if you want I can calculate this. This is something like that. How many people want me to calculate this? Only one person has the appetite? Okay. So this is an exercise, do it. People may ask you if you can do this. Then I can plug this in here, right? I can take the derivative of this. Derivative of this is going to be d squared dt squared x is going to be 1 over m d dt expectation value of p But now we have something for expectation value of p, and I can carry this m to here. I have m d squared dt squared expectation value of x is equal to expectation value of minus del v del x. This is actually a Ehrenfest theorem. So expectation values obey classical laws, but there is a little bit of problem here, right? Classically, we have m d squared dt squared, let me call it x classical, is equal to minus del v x classical del x classical. But now we don't have something like that, right? Suppose I have defined, let me define x classical to be expectation value of x, which is reasonable, right? What else can I define it? Then I should have here something like del v expectation value of x, del expectation value of x. But I don't have that. Instead, I have, if you want, expectation value of force here. And for that, we can think about force being a function of x and Taylor expand around wherever we want. In this case, I can Taylor expand around this classical position. What I can have is f x plus, so this is the lowest order term, f, let me write it like this, f prime x minus x prime plus 1/2 f double prime x minus x prime squared. And of course, higher order terms. But I'm thinking about small deviations from expectation value. Then, here, if delta x is negligible, if my uncertainty in x is small, I can drop this term. And if I drop this term, expectation value of f becomes f, let me call now is x classical, but this is, right, here, if I do the expectation value minus expectation value, right, I am taking the expectation value of whole thing, this thing is going to be 0, then I have the classical law, d m d dt squared x classical is equal to f x classical, and this is given by minus del v x classical del x classical. So basically what we are saying is like, yes, quantum mechanics is not like classical mechanics, right? But classical mechanics emerges from quantum mechanics, assuming you have the uncertainties are small, right? Assuming the most essential piece of quantum mechanics, which is the uncertainty relation, is negligible, you should have the classical law. That's why we think quantum mechanics is more fundamental than classical mechanics, not vice versa. Okay? Any questions? Let me give you the code and finish it here.